Hello all, welcome to my course on methods of adhesion measurement theory and practice. We are at lecture 28 today and we are discussing about adhesion using cylinders. So, this is a brief description about the resources from which we have taken our topics, and in the last lecture we discussed about two cylinders with their axes parallel to each other in contact with adhesion, and this is the relation that we derived. And this relation, as you can see, is very similar to the J-Kerr contact mechanics equation for the spherical objects that we derived. For example, over here we have this F versus A data, and then we can obtain from this data by rearranging this equation, okay, both the work of adhesion, that is W here, and the modulus, that is K. So, how? So, that is what I will like to do. I will rearrange this equation. So, I will write F by square root of A, and that will be equal to 3 pi capital K L by 8 R, A square will be A to the power 3 by 2 minus square root of 6 K pi W A and L square. And so, let us say it is like this. Now, A by 3 by 2, that is fine, it is A by 3 by 2 by R, that also I can do. So, here let us say write it like this, A to the power 3 by 2 by 3 by 2 by R, and that is equal to the left hand side, and that is equal to, let us divide it like this, let us say it divided by like this, 8 R by 3 pi K L and F, or and R is not there, right. So, 8, right, F by A to the power half, and minus this is, let us say it is square root, and I take it in the inside. So, it will be 64 here, R is here, I will not do anything with R, and then here it is 9 pi K L, so K square and pi square also, no, all square, into 6 K pi W A L square. So, now L square gets cancelled, pi will be pi here, K will be K here, here it will be 3, so 3 2 here, and here it is the 2, here I will cut it to 3. So, we will have here therefore 8 by 3 pi K L F, no, it should be plus here, by square root of A, and there will be plus, and here it is, let us say 8, let us say inside only, that is fine, I think. So, it is 8 and W A, here it is 3 and K and pi, and like that. So, like this. So, here we have got, as a 8 should be outside here, therefore, if I do not put it inside. So, like that. So, basically we can now plot, let us say A to the power 3 by 2 by R as a function of this F by square root of A, and we can get the slope and then this intercept, from where we can get the work of adhesion. So, here the arranged, this is arranged a little differently, but the same thing, that we can get this, and we can get both the slope. So, from the slope we get here 1 by K, so that is the intercept. So, we plot, let us say F by L by A to the power square root, and here we plot A to the power 3 by 2 by R, 8 R with a coefficient 3 pi by 8, okay, and if you get straight line, the slope will give my this K here, and the intercept I will get here like this. So, this is the idea. So, yeah, like that. So, now today I will like to start talking about hysteresis and how we can use this, again this cylindrical geometry to measure these hysteresis, to estimate hysteresis and like that. Now, hysteresis come to us in many different forms. So, I have a small movie here to show you that this is called contact angle hysteresis. So, a liquid drop is being dispensed using this needle over here. So, using this needle, okay, this little drop is being dispensed, okay, with a hydrophobic surface. Let us say this is water, let us say, and you will see that the contact angle during the advancing and the receding are not exactly same. So, for example, here the contact angle increases, and because this is, let us say over here, the contact angle actually in increasing. So, in this region we can measure this contact angle will be something like this. This is the theta advancing. So, this angle, okay, you will see that this is actually different from the angle over here, let us say, when it is receding. So, let me go back here. So, you can see here in the receding phase the contact angle is actually much smaller. This is the contact angle during the receding phase, theta r. So, theta r a, okay, is actually much greater than theta r. So, this is actually called contact angle hysteresis. Okay. The surface might appear hydrophobic in the advancing stage, but when receding it is not exactly showing that hydrophobic behavior. So, this is a example of contact angle hysteresis. We can see the manifestation of contact angle hysteresis or surface hysteresis in some other case as well. For example, over here, let us say this is an inclined plane, and on that a drop is has been suspended, and here you can see that the drop remains pinned to the surface. So, this is the line, contact line, and this is the contact angle in the advancing stage, and this is the receding. Okay, the receding angle will be somewhere here. So, this advancing angle is much larger once again than the receding, and in fact, the drop remains pinned in the sense that the difference between advancing and receding may not be that large, but the drop does not slide down. Okay, even if this surface, okay, is being lifted in from one side. So, then also the drop does not slide down over here. So, you can see that this is being actually pulled in the other side, but still the drop, okay, this angle difference between increases, but it remains pinned over here. So, again this kind of surface which may show high large contact angle, okay, has got very high hysteresis, and as a result the sliding angle is also quite high. They cannot be called a super hydrophobic surface, they are simply hydrophobic in the advancing case. In the receding, the angle may not be even hydrophobic or less than higher than 90 degree or like that. In contrast, I will show you another movie here in which the drop is being dispensed on a surface, and you will see this is a high speed movie, high speed camera picture. The drop collides and then it actually bounces back, okay, and with a little inclination on the surface, this drop actually goes out of this position, so gets cleaned up. So, this is an example of a super hydrophobic surface where the hysteresis is actually rather quite low. So, like that. So, now we are not talking about contact angle hysteresis, nevertheless I presented this videos to give you some general idea of hysteresis. Now, hysteresis we will discuss by a very simple experiment shown here. So, in a sense we have got a solid substrate, let us say, and then let us say we have this elastic cylinder. This elastic cylinder is placed in contact, and then it is we achieve some finite contact width. Therefore, okay. So, let us say some finite contact width is achieved, and this contact width with respect to pressure P, that can be related. So, if I look at from this side, it will look something like this, that the cylinder over here, it is deformed somewhat over here, and the radius, the width of the contact, okay, will be a 2a over here, and this is of course the width. If you see from the top, the contact width look, okay, parallel lines like that. This is the contact width, it will look something like this. We have worked on this kind of problem. So, we can apply load, and if there is adhesion, then we can apply the pulling load, pull off load as well. So, at a critical pull off load, this particular cylinder will come out of this surface. So, that is the idea. So, that is what we have done so far. So, here for example, that when we apply load, there is vertical displacement, and this we have done. So, if delta is the displacement of this point of application of this load over here, that is the cylinder. So, the point of application moves by a distance delta. So, it has gone within this this particular point has moved by distance delta, okay. And then the vertical displacement at any other point is actually delta minus x square by 2r, that we have done. And so, therefore, we can write del v by del g, that is the grad del v by del x, that is the gradient or the slope of deformation, that will be minus x by r, okay. And we know that we in the very first few lectures, I think lecture 3 or no lecture 5 or 6, we had derived this expression, that where this pressure integral, this integral is related to this shear stress and this gradient in deformation. So, this is that slope or gradient in deformation that we had derived, this equation we derived earlier, gradient of vertical deformation. Now, over here there is no friction. So, qx is equal to 0. So, that we know. So, qx is 0. So, we have this. So, we have therefore, it is minus, this is pi e by 2 into 1 minus sigma square Poisson square, and this is minus x over r. So, this quantity is equal to, therefore, this is pi and sorry over that pi, and this is E star by 2, and this is x by r. This is the form. So, this is the way that we get when we just have compress it and release it like that. So, this we have done. Then we get the pressure distribution, okay, in this particular form of this, we replace this function g s over here. So, this is, we call it some kind of like this function, we call it g over s. So, g over s we replace it over here, okay, and we can obtain the so the solution of this kind of equation, general solution that is available, we have used it earlier to obtain the pressure distribution. Now, how do we determine the hysteresis? Now, what we do is, at this state when we have applied some amount of load, we let us say we apply torque over here. So, the torque we apply, so the cylinder will now try to roll. So, what happens? Let us say that torquing has been applied by this kind of an experiment. So, let us say it is not just complete cylinder, but let us say this is a half cylinder, okay. Let us say this is a half cylinder which is brought in contact, and the advantage is that we can put a thin plate, okay, or a very light thin plate, and we can apply, if we want, we can apply some load over here, or we can just leave it like that, and because of its adhesion itself, this comes in contact, or we can apply small load. And then what we do is, we can use this particular plate on top that allows a torque to be applied easily. So, we apply a torque. So, when it apply a torque, this cylinder will try to roll over here, and as a result, when it rolls, so think about it, that this is the cylinder, and as it tries to roll, so from here, this position over here, so what happens is that in this region, okay, the crack actually opens, and in this region crack actually close. So, this region, okay, I call it advancing crack, okay, and in this region it is receding, okay, that is the way that happens, okay. So, this is advancing and this is receding. So, very similar to that advancing contact angle and the receding contact angle that I had discussed a couple of minutes back. So, this is what it happens. Now, when we apply, when we try to roll it, it so happens that if there is no hysteresis in the surface, then the force that will be required to advance to close it, okay, that will be force that will be required to recede it, that means to open the crack over here, okay. So, that load that is required, okay, that will be compensated by the load over here. So, the torque applied will be actually equal to 0, we do not need to apply any torque there. But however, if that is not the case, there is a hysteresis there, then what happens is that the contact width that changes from B0 to B here. So, B0 is before rolling, okay, and when we apply the torque and let us say there is hysteresis, the contact width changes. Now, another something else also happens. So, the contact width changes, and if you see it from this side, the contact will look, the cylinder deformation will look something like this, okay, under optical microscope. So, here what we will see is that there is stretching okay, in this portion where the crack is tending to open. So this is the receding side and this is the advancing side, and as a result there is asymmetry that happens. So here the contact was symmetric, as you see it is symmetric over here, but over here because of this hysteresis there is an asymmetry that over here. So the pressure distribution has to now negotiate with this or has to be, we have to calculate this pressure distribution considering this asymmetry. So the contact width now goes from minus beta to alpha, okay. So that is the way it will look like. So over here when it was symmetric we had or the pressure distribution we have to find out, so pressure distribution function will be like this, and so that will lead to, okay, this kind of a geometry, this kind of a variation of the deformations, the gx function, and here the contact width goes from minus beta to alpha. So that is the way it happens. So now therefore this equation that we have it here, okay, this equation will have a asymmetry. So this is the equation, for example this equation will be used for finding out the p over p of x. So there, okay, we have this asymmetric function. So here minus beta to alpha that goes, but we can simplify this, that is what I will like to discuss here. So let us substitute this kind of expression, alpha plus beta by 2 is equal to b and alpha minus beta is equal to d here, and so therefore if you see alpha, so using these two equations, okay, so if I sum it up then I get 2 alpha, so it means alpha, so alpha, so to sum it up it will get b plus d, right, and then if I subtract from b minus d, so it is b minus d. So if I subtract this quantity minus this quantity, alpha plus beta by 2 minus alpha minus beta by 2, so it will be 2 beta by 2, so beta is equal to b minus d here. So that will get. So we can substitute this expression, so we can get this alpha is equal to b plus d and alpha is equal to b minus d, and then we can also take care of this limits. For example, I substitute x is equal to r plus d, and so x is equal to r plus. So now at x is equal to minus beta, therefore, so minus beta will be equal to r plus d. So r, okay, r is equal to minus beta minus d. So minus beta minus d, so that will be equal to over here. From here you see that beta plus b will be equal to beta plus d, so minus b will be minus beta minus d, so this is equal to minus b, and x is equal to alpha, so here it will be alpha is equal to r plus d. So here therefore r is equal to alpha minus d. So you see here from here, okay, alpha minus d, so it is alpha minus d is equal to b. So therefore, okay, by having this transformation or this kind of substitution and this substitution, we can actually convert this asymmetric equation into a symmetric one. That is what I would like to show you. So here for example this was the asymmetric equation that we have, and now we have changed this. So what we will do is that instead of having x we will have r plus d. So actually the pressure will come in terms of r here, and so here it will be pi square, and then we know that x plus b will now will be equal to b, we have symmetric now in terms of b here, right, in terms of b we get the symmetry. So it is this is minus b to b, so it is b in terms of, so therefore it will be, so r plus b here, and here it will be b minus r 1 by 2, then it will be minus beta, so it will be minus b plus b, and here it will be, it is s plus b, and it is b, so it is b plus s into b minus s, so it will be b square minus a square, okay, and half, and here it will be r minus s, okay, like that, and this is pi e star by 2r, instead of s we will have s plus d here, because all these things are happening because we are using this substitution. So it will be like that, and then plus as it is we have c, and this is pi square, and over here this is b plus r and b minus r, so it is b square minus r square square root, like that. So, this is what, and we know that symmetric, for the symmetric expression we have the solutions for this integral and we will use that. So, 1 by this is pi square and this is b square minus r square and this is square root and this is minus b to b. So, here let me write it minus b to b here, and yeah, actually I can write here pi e star by 2r, I can take it out. So, it will be pi e star, here it is 2 into r here, and then here it is, actually let me try it a little bit clearly over here. So, it is 2 into r and let me write it over here bracket, okay, and then it is minus b to b and here it is a. So, it is b square minus a square, it is half, and here it is r minus s and here it will be s. Oh, sorry about that, here I should have the ds. So, ds will be there and then plus it is d into, then here I have minus b to b and here it is I have b square minus a square by r minus s and it is ds, yeah, like that, plus it is capital C by pi square into b square minus r square to the power half. So, that is all I have and that is all it comes out to be. Here it is b square minus r square here, and now this is the way the equation comes. So, I have here this quantity which I call I1 with a coefficient b square. So, and here I called it I0 with a coefficient b here. By the way, there is a d I have missed somehow here, I think that I should not miss. So, no, d I have written, okay, correct, no, I have d written, okay. So, here it is like that. So, now we have to use this solution. Now, here remember this rho is in terms of r by b. So, this solution is in terms of this non-dimensional quantities. So, dimensionless length here rho, and so we can easily use it. So, for example, for n is equal to even or 0, so that means I have to use this equation. So, from here I0, okay, it comes out to be will be pi, and let us say this is rho here. So, it is n is equal to rho, so it is r by b. So, I have to write here r by b, yeah, that is it. And for here I1, okay, I have to write pi and here n is equal to 1. So, it is odd. So, it is r by b whole square minus this is half and this is n is equal to 1. So, it is 0 there. So, that is it. So, like this. So, now you substitute this expression over here. So, it will be p of r, it is minus, it is e star by 2 pi r and this is 1 by square root of b square minus r square. Here I write b square into I1. So, I1 is pi and this is r by b whole square minus half, and then plus I write, by the way I should write like this, fine. So, plus let us say I1 is d, here is b, I1 is pi, it is r by b here and square root of again b square minus r square, and then I have got the c. So, c comes out to be capital P into pi divided by pi square and square root of b square minus r square, like this. So, here we gets cancelled, pi gets cancelled, and then this b here, this b square will go. So, finally, it will come out to be, let us say this is p over pi into square root of b square minus r square, and then minus it will be e star by 2 r square root of b square minus r square, okay, into here it will be b square, so r square minus b square multiplied by that. So, it is b square by 2, it is plus, it will be d into r, and then yeah, that is it. So, like that. So, this is the way the pressure distribution that will be there in terms of R, B and D, and this is the way. So, that is all we have derived here, and then is like that. So, now the pressure is given by this. So, the stress that is developed will be negative of that. So, here it will be like that. So, now remember that this is an asymmetric situation that we have. So, as a result the stresses at the near to the crack tip or the two edges are not exactly same. So, the kind of stress profile that will be there will be different from the stress profile over here, and that actually is because that it actually leads to this hysteresis, and that is because of this hysteresis. So, we will like to figure it out that what kind of stresses are there. So, at the receding angle sigma r at r tends to b. So, here this is E star, this is 2 r, this is square root of b minus r into b plus r, and over here again this is r square minus b square by 2 plus d into r, and this is at r going to b minus this is p into pi, again the same way square root of b minus r into b plus r. So, in all the cases I put r tending to b. So, that will be is equal to, so this is the receding angle where the crack opens. So, it is r plus r going to plus b. So, here it will be E star, it is 2 r, and here it is r plus r is 2 b here. So, I should say equal, not equal sign, almost equal to something like that. So, it is 2 b into b minus r, and here instead of r we put b here. So, b square minus b square by 2. So, it will be b square by 2 plus d into b here minus this is p by pi, again the same thing, this is b minus r into 2b here like that. And so, therefore, I can write it like this. Let us say I write here 1 by square root of 2 pi into b minus r, b minus r. So, that will be minus p, this is square root of 2 pi. So, it is square root of 2 pi. So, it is p divided by square root of p into pi, b into pi, right, b into pi, right, and then plus, and over here again E star, and here it is square root of this is 2 and pi has been taken. So, another pi will be there. So, if the pi I take here, so let us say I take pi into b, okay, and here I think I need to have a pi therefore, and then I will have b square by 2 plus d into b like that. So, in a sense what I am trying to get is the stress intensity factor in the receding edge. So, I will continue this discussion in the next lecture. Thank you for your kind attention.